Hi, let us continue with the analysis of the circuits. So maybe in the previous video we have seen MOSFET as an amplifier. I hope you can understand that okay, we had a small signal. It was not possible to amplify that signal by directly connecting it to the gate. So then we connected through a DC source to shift the waveform from 0 to some DC voltage, and then we could able to write its AC equivalent model by shorting that what DC voltage sources. This has been shorted and this has been made ground. This is what is the immediate equivalent circuit. Then we replaced this MOSFET by its AC equivalent model, which is being represented by a open circuit between gate and source. Between drain and source we have a current source whose current depends on GM into VGS, and of course this is RD which is connected here, which will be in turn connected like this, and since this is ground, this is also ground, we are just connecting it from drain to ground. Now and of course we also obtained an expression for the output voltage, which is nothing but suppose if you assume a current of I0 here, this current I0 is nothing but negative of this GM into VGS. That's why it is GM into VGS, and that VGS is exactly V, and we obtained the expression for gain of this amplifier as minus GM into RD. We can actually name this amplifier. uh, for naming ceremony we will try to see. So this is our input, this is the output. Now you can see we are measuring the input at the gate with respect to ground, and we are measuring the output with respect to ground. So out of gate, drain and source of the MOSFET, which term is grounded? So source is actually grounded. So source is actually grounded here, meaning to say, is this source common between input and output? Because I'm measuring output with respect to source, I'm measuring input also with respect to source. So we call such type of amplifiers where input and output are measured with respect to source as common source amplifier. So what is the name of this amplifier now? It is called as common source amplifier. So why it is called as common means, so this source terminal of the MOSFET is common between input and output. So that's why this amplifier is named as common source amplifier, or in short it will be said as CS amplifier. CS amplifier. So C stands for common, S stands for source. This is CS amplifier. And we have seen that we need to connect some DC source VGS, which was 0.6 in the previous case when we actually did it. But that is not a good way of designing or biasing the amplifier. So let us see how do we redo this, because the ultimately what you want is you want to have a DC voltage and this input signal should be reaching the amplifier. So instead of having this, so we will retain this part of the circuit as it is. So you can see here I am retaining this circuit as it is here. This is RD, this is what is VDD here, and I'll have the input also as it is. So this is my input, so I'll connect it. So now this is input, this is the output point. Now this VGS should be obtained here, so that VGS will get it from this VDD itself. So I will connect a potential divider. You can see now this is connected here, this is connected here. I will say it as R1 R2. Now this R1 R2 is connected in such a way that this VDD and R1 R2 will give me the required VGS here. So using your potential divider concept, suppose if you have a VDD here, suppose if you have a VDD here, if this is R1 and R2, if you want to know what is this voltage Vx, so can you see, is this actually VDD connected? Of course, what I can do is I can also connect it this way. This is my VDD. So instead of putting only VDD here, I just put VDD here. So what I'm doing is I'm just taking out this R1, R2 and VDD outside. Then what is Vx? Because this is ground, I'll put a ground here. So shall I assume a current of I in this loop? This is the current I. So what is that current I? I know that current is I is nothing but voltage by resistance. So what is the resistance? It is, since the resistance of series, it is R1 plus R2. So what is the current that is flowing in this loop? It is VDD by R1 plus R2. If this is the current that is flowing, then what is this drop? Because this drop is nothing but Vx. So I can write Vx as I into R2. So I can write finally Vx as equal to VDD by R1 plus R2 into R2. So what is this now? This is the voltage at this point. So is this point same as this point here? So can I now write VGS here? VGS, can I write it as VDD into R2 by R1 plus R2? So this is the voltage. Now this whatever battery you had separately, now that is been removed and you're getting the desired VGS using the same battery which was connected here for VDD. I'm using same and deriving the required VGS. Now you have this AC signal. This AC signal should be shifted from, now we know that this is, if this is my IV characteristics, this is VGS and this is ID. Here I'm applying the signal, so that should be shifted here. So that should be shifted. So this shifting has to be done. Now this is actually this voltage, so that I will going to couple it using a coupling capacitor. So this I will name it as CC. So this suffix C corresponds to coupling. What you are coupling? You are coupling the AC signal to the amplifier. You are coupling the AC signal to the amplifier. That's why the name of this capacitor is coupling capacitor. We know that the capacitor reactance Xc of the capacitor is 1 over 2 pi Fc. Suppose if this AC signal has some DC, that DC will be blocked by this coupling capacitor. That DC will not affect this VGS. Whereas AC signal, for AC signal of the input, this almost act like a short circuit, because as the frequency increases, this Xc will reduce. If Xc reduces means it acts like a short circuit. So effectively this coupling capacitor is used to couple the AC signal and block the DC, so that this DC, if at all, if it is available the input, should not affect my biasing voltage VG. Yes. So what is the purpose of this R1 R2 connecting to VD and this gate terminal is to realize VGS, Maybe in the previous case we have used this as 1K, this as 1.8 volt, and this was 0.6, and then I think we applied some 100 millivolt input signal. So let us realize same 0.6 volt using this R1 R2 and VDD of 1.8. So let us do that. So what I'll do now, so I will rewrite the circuit. This is my input, there is a coupling capacitor, and I have this resistor R1 R2 connected to the gate in this fashion, and then I have a resistor V0, this is V0, this is VDD coupling capacitor, Vin, ground this R1 R2 RD, this is my capacitor, sorry, MOSFET. Of course MOSFET will have Kp of 200 microampere per volt square, VTO of 0.4 volt, and you can assume W by L as 1000 micrometer by 10 micrometer, which is equal to 100 now. So let us assume a VGS of 0.6 to get 0.6 here. So what is that VGS expression? VGS is equal to VDD R2 by R1 plus R2. Since this is 1.8 volt, we are assuming, let me find out R2. So this is 0.6 required. So let me assume R1 as some 200k, and this again R2. So in this expression, you know this, you know how much you want to get. Let us assume this as 200k. So we can find out what is R2 is. Again, no need to simplify the equation, just feed the equation as it is. 0.6 alpha equals, open the parenthesis, 1.8 into, this is a variable, alpha a divided by, again open the parenthesis, it is 200 exponential 3 plus, how much is this? This is again alpha a. You can see this is the equation I have fed. Close the parenthesis, close the parenthesis. Just see it again. So I'm just feeding this equation as it is. 0.6 alpha equals, you can see, open the parenthesis. I'm actually doing it like this. Open the parenthesis and this whole divided by, maybe what you can do is you can just okay, this is divided by, and you have this. Maybe I may have to just give only one parenthesis, or I think I need to give two. Fine. So now what to do? I have to do shift cal. You can see you are having it as 100k. So in order to exactly know what is this, you can press this engineering. You can see it is 100k. So R2 value is equal to 100 kilo ohm. Meaning if I'm using this as 200k, then this should be 100k, so that this will give me 0.6 volts. 0.6 volts. So once you get 0.6 volts, so you can able to, okay, now this is going to give 0.6. Shall we write the AC equivalent of this? So what is the AC equivalent? You replace this by ground. So this is how you're writing now. I'm writing this. So this is my AC equivalent circuit. You can see I'm grounding this. I'm grounding this also. This capacitor will be considered as a short circuit for AC analysis, because let me just explain that. What is the reactance of a capacitor? It is Xc is equal to 2 pi Fc. Usually for a AC signal, frequency we are considering it as very high. For a AC signal, when the frequency is high, is this denominator very high? When the denominator is high, we know that Xc is very small. So what do you mean by Xc small? That is, reactance offered by this capacitor is negligible. So when it is not offering any reactance, there is no resistance. There is no resistance means this capacitor will be treated as a short circuit for AC small signal analysis. For AC small signal analysis, this capacitor will be treated as a short circuit. So you have a capacitor, you short it, that is, you don't write that capacitor. So that's exactly nothing but Vin. Sorry, this capacitor not considering, this is as well as representing short. So I'm writing Vin as it is. So this is my Vin. This is R1, R2, this is RD. So now what is next step? Now since it is, now let me rewrite this MOSFET as, now what should be replaced? This should be replaced by, this should be replaced by something like this. Correct? This is gate, source, drain. This is what? GM into VGS. This is plus minus. So this is your gate, drain, source. These three terminals are replaced by this. So I will write it now. you have the input. This is your R1, this is R2. Can you see this is gate? Can you see this is GM into VGS? This is GM into VGS. Can you see this is drain? Shall I say this is RD? This is R2. This is R1. Shall I short these two and connect it to ground? Is this is my V0 point? Is this is my V0 point? Is this my V0 point? This is drain. This is source. Shall I short the source? Sorry, this is source. This is gate. This is drain. See, I had this circuit. Replaced this by its AC equivalent. This DC source is grounded. This capacitor is replaced by short circuit. Because of this reason, I'm replacing the MOSFET by its AC equivalent model. So now let us simplify this. Can you see this point is same as this point? If these two are same, shall I just flip it down here? If I flip it down, this is how the final circuit will look like. This is V in. So this is that point. Gate, to the gate, do you have a resistor R2 between this and ground? So this is between gate and ground. Can you see this R1 is also between gate and ground? Shall I write this as R1 now? Can you see this R1, R2 which are like this will look like R1, R2 parallel. Then is this, okay, I'll write the current source as it is. This is my current source. This is now GM into VGS. What is this now? I have this as my, can you see now this is coming down here. So this is the ground, that's the ground. Can you see this RD is connected between drain and ground. So this is again drain and ground. So this is RD. So this is what VGS is, plus minus, correct? Now let us try to find out what is the expression for the output voltage. So let me rewrite that circuit diagram what I have written. Because of constraint in the space, I'm just rewriting. This is R1, this is R2, this is gate, and I have the drain. This is GM into VGS, and this is RD. This is ground here. This is V0. This is V in. This is plus minus VGS. This is R1, R2. This is RD. So let me assume a current of I0 flowing through this. So is this is the equivalent circuit of this amplifier? So this is the AC equivalent circuit of the CS amplifier. Shall I write it as AC small signal equivalent circuit of CS amplifier? Again, how you're defining this as CS amplifier? Can you see this is source common for both input as well as output. So you are measuring the input with respect to source, you are measuring the output with respect to source. So this is plus minus, again plus minus. When I say minus, it is with respect to source, you are measuring input as well as output. So that's why the name common source amplifier. Now let us try to find out the expression for V0. So what is V0 expression? It is I0 into RD. It is current flowing through this resistor multiplied by resistance. So this I0 is nothing but is in the opposite direction of GM into VGS. So it is minus of GM into VGS into RD. So this is what I have. Now what is this VGS? Can you see this is VGS? Is this VGS is same as V in? Here this is VGS. So even though resistors are there, the potential across a parallel component parallel of the circuit always remains the same. So this VGS is equal to V in. So then in such case, can I write V0 is equal to minus GM RD into V in? Therefore, can I write gain of the amplifier, which is nothing but V0 by V in, as minus GM RD. So what is the expression for the gain? AV, voltage gain, is nothing but minus GM into RD. That means to say, whatever expression you had it earlier for this amplifier, which was minus GM into RD, you still get the same thing. Only difference is that this VGS, which was realized using a different battery of 0.6, is now being replaced by two resistors of 200k and 100k, and these two along with VDD is giving the desired voltage. And this coupling capacitor is used to couple the AC signal to the amplifier. So the role of CC is to allow the AC signal to this, but block the DC signal from going through this capacitor. Because DC is blocked, because frequency is 0 for DC, then XC becomes infinity, meaning it doesn't allow, it will not allow the signal. So let us realize the same thing over here. So let me just do it quickly. If I have that amplifier, fine, otherwise I think I have it. Yeah, I have it here. See, yesterday we did it. We have this. Let me just take all these things appropriately. So this amplifier. Now let me replace this by two resistors. Let me save it as one more file. This is CS amplifier. Now what I'll do, I will slightly minimize this. I will pull this slightly this side so that I can able to comfortably do the things. I will pull this also. Okay, now let me take two resistors such that I can eliminate this. Okay, how do I eliminate? This is my scissor, or you can press this F5 function 5. I have taken out this, then let me short it. So you have a wire F3. Next I will put a capacitor as coupling capacitor. Let me rotate it, Control R. I have placed it here, and then let me make this zoom full extent. This is zoomed. Now let me connect the wire. You can see now this is R1. Okay, I will stop it here so that node is created and put it down, and let me just connect that resistor exactly in line. Okay, now this is fine. Can you see this is okay? Let me name it as some RD so that it just exactly follows the naming what we have in the. Let me name it as R1. Otherwise that naming will be different from my circuit. Let me name it as R2. So this is R1, R2 and RD. Let me replace this by 200k. Let me make this as 100k, and this capacitance value, let me use it as 0.1 microfarad. This is done. So let me first do .op. .op should give me, okay, let me also label this as VGS. VGS is the voltage at gate and source. Let me connect these two and this. Okay. So VGS is actually 0.6 because of this VDD and R1, R2. Let me do .op here, DC operating points. Okay, now if I do this, see now VGS is equal to 0.6, and it is giving current of how much? 400 microampere. This 400 microampere dropping here will give me a drop of 0.4 volt. So out of 1.8, if 0.4 goes, you are left with 1.4. So this is the voltage at drain. So this is the DC voltage at drain, and this is the DC voltage at gate to source. Now with these specifications I should get, let us see how much is GM. So how do I see GM? With the same .op, you can go to this view, look for this SPICE error logs. See, now this is GM. So let me just put it side by side. What is GM and RD, how much you're supposed to get. So GM as per our calculation is 2 ID Kp W by L. So as per our earlier yesterday's calculation, this should be 4 millisiemens, which is actually 2 into 400 micro into 200 micro into 100. So this should be 4 millisiemens. So let me find out. It is under root of okay, let me just do this. Under root of 2 into 400 exponential minus 6 into 200 exponential minus 6 into 100 close equals. You can see this is 4 millisiemens. So I have 4 10 power minus 3. So it is 4 millisiemens. What is AV? It is minus GM into RD, that is minus 4 milli into RD is 1K. This K and milli will go off. You'll end up with minus 4 volt per volt. So this is my AV. This is the gain of that. So now let us go back here. So now let us do dot tran. Dot tran is transient analysis. So as we discussed in the last video, in order to get maybe 3 cycles, what should be the time, all those stuff. So you can see this is what we discussed last. See, this is if the frequency is 10 kilohertz, then time period for one cycle is 100 microsecond. If you want to see 300 microsecond, sorry, if you want to see 3 cycles, it is 300 microsecond. So now let us see 5 cycles. So for 5 cycles, this should be 500 microsecond. Make it 500. This is done now. So I will see 5 cycles. Let me run this. You can see this is my input signal. You can see 5 cycles, 1 2 3 4 5. I can see what is output. So you can see output is around 1.4. It is keep oscillating there. If you want to see this is now I have to get a gain of 4. Let us see what is input peak to peak. Input peak to peak is 20 millivolt. Oh, I just put it back. So this is input peak to peak. Can you see it's almost 20? Let us see output peak to peak. So now what is input peak to peak? Let me just see this here. So V in peak to peak and V naught peak to peak. So this is 20 millivolt. This is, let us see how much. So I have this as, how much is this? If you can see here, this is that peak to peak, almost 80. This is 80 millivolt. So what is here? Can you see this is almost 80 divided by 20? So this is equal to 4, because this is the magnitude. That negative sign, as we discussed in the last class, it is out of phase analysis. We're going to do it. So what we are trying to demonstrate here is we can able to realize a CS amplifier using a potential divider biasing. So this is effectively called as, this potential of 1.8 is divided in such a way to achieve the desired VGS of 0.6. So that's why the name of this amplifier is CS amplifier with potential divider biasing. So let me just write it here. This is what. So you have a CS amplifier with potential divider bias. So biasing that is required to move the input voltage. This is what we are discussing in the previous video. So I want to move this from this to a VGS point which was 0.6 is done using this potential divider. So where is that? This potential divider.